Assalamualaikum and very good morning to all of you. So for today's lecture, we are going to continue with the new chapter, chapter 6. The title of this chapter is Optical Noise in Receiver. So this is a continuation basically from the receivers topics that we have learned in chapter 5. If you can recall, in chapter 5, we have learned about the fundamental of optical receivers, yeah, to be specific on the photodetectors, the photodiode. And we have learned about the uh, working procedures of these photodiodes, which include the PN, yeah, photodiode, PIN photodiode, and also avalanche photodiode. Okay, so these are the things that we have learned in chapter 5. So for chapter 6, this continuation, we're going to continue, in which we're going to learn on the noise, yeah, the noise that is produced in these optical receivers, in which this is very important, particularly because it will enable us to calculate the signal to noise ratio, yeah, signal to noise ratio of your receivers, yeah, optical receivers. Okay, so this will be the content of this lecture. So we're going to have a first will be on the introduction to noise. Okay, then we're going to see the type of noise that can be generated in optical receivers. Following that, we're going to see the noise that exists in PN and also in PIN photodiode. So basically, our lectures for today will be ended up to this topic. Yeah, and part 2 of lecture 10 will be continued later. Will on this topic of noise in avalanche photodiode. So that will be the part 2 of lecture 10, and subsequently you're going to see on the calculation, yeah, calculation of the signal to noise ratio for these photodiodes that we have. Yeah, right. So basically, this will be the content of our lectures. Okay, and we're going to compare this with the CI that we have. So from the CI, basically, it's very simple. It states here about the receiver noise consideration, okay, and calculation of signal to noise ratio. So that will be the topics, yeah, the topics in general that have been stated in the course information. All right, so let's continue further. All right, so regarding the noise, I believe that you have understand this very clear. Yeah, when you learn about the principle of communication, basic com, yeah, in year 3, semester 1, I believe that the first chapter of this course of basic communication is on noise, right? So the ideas was there, I believe, yeah. So we're going to repeat, to review about the noise related matters. So we know that noise is as any signal, yeah, which is not man-made, yeah. So it is naturally produced, okay. So it present in the receivers, yeah, other than desired signals, okay. So it means that apart from desired signals that we want to have, we want to transfer, we want to transmit, we also have the noise, yeah. Right. So basically, this noise will create the unwanted disturbance that we don't want. Yeah, in which the effect will be it will corrupt and degrades the information content of our desired signals. Yeah. So these are the effect of noise that we don't want actually. Yeah. So it will set a lower limit. Yeah, lower limit on the amount of optical power required for proper receiver operations. Okay, because when we have a noise, yeah, it will degrade the signal, and subsequently the amount of optical power that will be required, yeah, for the signals recovering, yeah, recovering will be smaller. Okay, so basically it will degrade, yeah, it will corrupt, it will then reduce the amount of optical power that can be received or that can be that is required, I can say, for proper receiver operations, right? And we need to actually know, we need to actually understand what are the origin of noise, okay, so that we can characterize we can then determine, or we can design in such a way that the optical receiver performance can be improved, yeah, by knowing these origins of noise. And then the sensitivity of the optical receivers, yeah. So basically, the amount of noise present will determine the level of sensitivity of our optical receivers. Yeah, that's for sure. Okay, there are two important parameters that we need to know before we can learn further about the noise related parameters. Okay, these two parameters are the signal to noise ratio, the SNR, and also the noise equivalent power. Okay, so we're going to see this one by one. So this is about the signal to noise ratio, SNR. So it is defined to be the power signal to noise ratio at the output, yeah, of an optical receiver is defined by this. So S over N is signal power from photocurrent, okay, signal power from photocurrent, okay, divided by the photodetector noise power and amplifier noise power. So basically, if we base on this, the signal that we consider in this particular case is signal power from the photocurrent, okay, from the photocurrent. So photocurrent is IP that we have learned in the previous like chapter 5, okay. So we have to calculate what should be the signal power, okay. So basically equation shall be I squared of R, okay, and also this is the photodetector noise power and amplifier noise power, okay. So we can have two types of noise power. The first one is from the detector itself, another one from the amplifier that is contained, that is exists, yeah, that need to be in your photodetector circuit. Yeah, so the amplifier, both amplifier and the photodetector will create the noise. Yeah, and basically the noise due to this photodetector and amplifier is characterized by this current, yeah, by this current, which is known to be the mean square, yeah, mean square of noise current, yeah, mean square of noise current, right? So this will be the symbol of mean square noise current, and we can calculate the power by simply multiplying this mean square noise current with the resistance of R. Okay, so that will determine the total noise power. Yeah, I squared noise times R will be the power of noise, and we can cancel out the R here. Okay, and then we're going to have that the signal to noise ratio can be calculated by simply have a ratio between the I squared P. So P stands for the photocurrent, yeah, stand for photocurrent, and I noise is the RMS value of the noise induced current. So as what we have discussed before, yeah. Okay. So it means that if based on this definition, yeah, for the I noise, you can see that I noise squared is a mean square, okay, mean square value. So I noise is root mean square, yeah, root mean square of the noise current. Okay, so that's what determine the signal to noise ratio for our case, yeah, for our photodetector. Okay. Number two is about the noise equivalent power, the NEP. So this noise equivalent power is defined to be the amount of incident optical power, the P naught, yeah, which is necessary to produce a photocurrent of the same magnitude as total noise current. Okay, yeah, so that should be the definition of the NEP, which is again, it's amount of incident optical power, the P naught, that will be necessary to produce a photocurrent of the same magnitude as total noise current, which means that a P naught in such a way that it will produce a photocurrent IP, which is same as I noise. Okay, so that's what meant by the noise equivalent power. Yeah, the photocurrent produced by the P naught is the same as the value of total noise current. Yeah, that mean the root mean square of the noise current. Yeah, so if we base on definition of SNR just now, okay, SNR equals to IP squared over I noise squared. Okay, that should be definition of SNR just now. So when we have the IP and I noise the same, so we're going to have that the SNR value is equals to 1. Okay, so for the NEP, it is the power the incident optical power, yeah, incident optical power, which is the incident power to your detector, that will then produce the SNR, yeah, of your receiver to be equals to 1. So that should be what meant by the NEP. Yeah. Okay, so basically, the NEP determines the weakest optical power that can be detected in the presence of noise. Yeah, so that's what meant by this, yeah, because it believed that the amount of its optical power, yeah, produce a photocurrent of having same magnitude of the with the total noise current. Yeah, so IP equals to I noise that we have stated just now. So that should be the weakest or the smallest optical power that can be detected. Yeah, because it will produce the amount of current which is same as the noise current. So that should be the definition. Yeah. Okay. So this will be the equation for the NEP, which is equals to P naught. Yeah, P naught is the power itself. Yeah. So noise power is the P naught, which will give us the noise current divided by the responsivity. Okay. And we have, as what we have learned just now, noise current is the equals to the output photocurrent. Yeah. So for this, we can say that the P naught, the NEP is equals to IP divided by the responsivity, which is NE lambda over HC. Yeah. So this is the responsivity that we have learned in chapter 5. Yeah. In which responsivity is defined to be the current, yeah, output photocurrent divided by the incident optical power. So that should be the definition of responsivity in chapter 5. You can check it back. Yeah? So that's why when we divide the IP over the P naught, yeah, I mean IP divided by the responsivity are going to get the incident optical power. So this responsivity, the equation is given by this. Yeah, you can check back chapter 5. Quantum efficiency, the eta, yeah. E is the charge amount, lambda is the wavelength, H is the Planck constant, and C is the speed of light. Okay, so by having a ratio between the IP and this responsivity, we can find what should be the noise equivalent power. Right, hopefully you understand about this NEP clearly, yeah? Okay, so that should be another important parameters that we need to know because it is related to the noise calculation later on. The first one is the capacitance of a detector. Okay, capacitance of a detector. So because we know that detector is made of a electrical circuit, yeah. So we're going to have the R, we're going to have the capacitance, yeah. So capacitance of detector is basically dependent upon the active area of the device. Okay, active area of the device and the reverse voltage across the device. So that should be the factors that affect the capacitance value. Okay, so that should be based on the equations that we have learned in EMT before. Okay, remember that we have a capacitance C equals to epsilon A over D. Remember, epsilon is your permittivity, A is the area, the area. So basically this A is basically this one, the active area of the device, and D is the distance between the plates. Yeah. Okay, and the reverse voltage, yeah, reverse voltage across the device. So this is the factors that affect the capacitance. Okay, because we know that from the equation of C, okay, C equals to Q over V. Okay, it's the same things, yeah. So V is the voltage applied across the capacitance, and we know that for a detector we are using the reverse voltage, yeah, reverse bias voltage. So that should be the voltage that will affect the capacitance value, yeah. Okay, so because based on this, we can write that the total capacitance to the front end of optical receiver is given by this. Basically, in your detector, in your receiver circuit, you're going to have two main components. The first one is your detector itself, the photodiode. Then we have the amplifier. So for each of these, it has its own capacitance value. So that's why we have for capacitance in total, it is given by summation of CD, which is your detector capacitance or the photodiode capacitance, yeah, and also the CA, which is your amplifier capacitance, yeah. So that should be the capacitance that give us the total value of capacitance in your optical receivers. Yeah. Okay. Number B, our second one is the bandwidth. Okay. So bandwidth is defined to be the maximum frequency or the bit rate that the photodiode can detect. Yeah. So that should be the definition of the bandwidth, the maximum frequency or the bit rate that the photodiode can detect. And basically, it is given by this equation in which there is an effect of the time constant RC. Yeah, B equals to 1 over 2 pi RL CT. RL is the load resistance of your receivers, and CT is the total capacitance that we have seen in the previous part, yeah, of this slide. Yeah, so CT is this one. Okay, CT is capacitance same as this, which is a summation of your CD detector capacitance and amplifier capacitance. So that will be the equations that determine the bandwidth, and basically the RC is referring or depending on the rise time, yeah, or response time. Sorry, response time. Okay, so we're not going to cover that into detail, but it's known to be the response time of your receivers. Yeah. Okay, so that should be the B equation, the bandwidth equation that can be used, yeah, in which it based on the resistors, the load resistors, and the capacitance. Okay, so if you base on this equation, we can see that the B can be increased, yeah, the B can be increased by reducing the RL and also the CT. So we can further reduce the RL, we can further reduce the CT such that we can have higher bandwidth, yeah? Because we know that higher bandwidth is very much required, yeah, in communication. But care has to be taken, yeah? Because if we reduce the RL, the effect will be the thermal noise will be increased. Yeah, thermal noise will be increased when we reduce the RL. So we are going to see later on in this lecture the effect, the relationship between the thermal noise and the load resistors. Yeah, but up to now we agree that if we reduce the RL and the CT, reduce the load resistors and the total capacitance of your optical receiver circuit, for sure the B will be increased. But reducing the RL will increase the thermal noise, which is unwanted. Yeah. Okay. Let's have a look at this example. So we are given a problem whereby a photodiode has a capacitance of 6 picofarad. Okay, capacitance C is 6 picofarad. We need to calculate what should be the maximum load resistance, which allows 8 megahertz post-detection bandwidth. Okay, so we are given that the bandwidth given is 8 megahertz. So we need to find the maximum load resistance that can be used such that with the bandwidth obtained is 8 megahertz. Okay, so again, we have to refer back to the equations of B equals to 1 over 2 pi of RL multiplied with the capacitance total. Okay, so we are given that the B is 8 megahertz, so 8 times 6, 10 power of 6 equals to 1 over 2 pi. RL is to be calculated, and total capacitance given to be 6 picofarad, which is 6 times 10 power of negative 12. Okay, so by calculating this, we are going to get that RL, the load resistance that we're going to get, shall be equals to 3.32 kilo ohm. Yeah, so that should be the maximum load resistance that is allowed. Yeah, that can be applied if we want to have the bandwidth of 8 megahertz of your optical receivers. Okay, second one is determine the bandwidth penalty with the same load resistance when the amplifier also has an input capacitance of 6 picofarad. Okay, so for this second part of the questions, we need to calculate any penalty on the bandwidth. Yeah, if the load resistance used is the same, which is 3.32 kilo ohm, but now the amplifier has been increased. Previously, the capacitance that we have is only from the photodiode itself, which is a CD, yeah, CD. But now we also have the capacitance from the amplifier, the CA. So the total capacitance now shall be equals to CD plus CA, which is equals to 12 picofarad. Yeah, because we have 6 from the photodiode and then the 6 from the amplifier. So that will give us the 12 picofarad of capacitance total. Okay, so for this, you're going to get that the bandwidth will be equals to 1 over 2 pi of the resistors used, which is 3.32 times 10 power of 3. And the capacitance total is 12 times 10 power of negative 12. So by calculating this, we are going to get that the bandwidth will be equals to 4 megahertz, in which we're going to have a penalty of 4 megahertz. Yeah, so initially, if we have 6 picofarad of capacitance, we're going to have 8 megahertz of post-detection bandwidth or the system bandwidth. And if we have additional 12 picofarad of your capacitance, so we're going to have a penalty of 4 megahertz, which will give us the bandwidth of 4 megahertz only. Yeah, so that should be the solution for this example here. Okay, so let us proceed with the source of noise for these topics. Yeah, so in optical communication system, yeah, in optical comm system, the noise can be actually generated by these phenomena. The first one is the noise from the light source. Okay, noise from the light source. Okay, noise from the light source here, in which this is of type extrinsic. Basically, it is a due to the laser intensity noise. Yeah, and basically due to this spontaneous emission of the photons. Yeah, so this is noise from light source. B is a noise from the light interaction with a fiber. Okay, so this is also an extrinsic type of noise. Yeah, and the third type is a noise from the optical receiver. So our concern is on part the C type. Yeah, is the third one. So we're not going to cover on this A and B because this is what we have done. We have did this previously. Yeah, on the light source and the fiber itself. So it's not in our scope of defining the noise for these two cases. So our interest only on part C, yeah, in which the noise due to the optical receivers or the photodetector circuit. So the noise is of intrinsic type, yeah, intrinsic type, and is associated with the front end receivers component, which are the photodiodes and the amplifier. Okay, so there are three types of noise that can be generated, yeah, by these optical receivers circuit. The first one is what we call as a thermal noise, or also known as a Johnson noise, which is found in the photodiode resistors, yeah, on the resistors part. Okay, that's why I mentioned just now that the noise, when you have a higher resistance load resistance value, the effect will be on the reduction of the bandwidth. Sorry, when we have lower load resistors, basically the noise will be increased. Sorry for that, the noise will be increased. Okay, so this is what we're going to see later on, yeah? Okay, number two is on the short noise. Okay, short noise in junction photodiode. And this short noise is due to the dark current. Okay, I believe that you have understand what is dark current from chapter 5. So dark current is the current that flows in your photodiode without any incident optical power. So we know that in chapter 5, when we have incident optical power, then only we can going to have the carrier generation. And so when we have carrier generation, then only the current will be produced in your photodiode. But the dark current is the flow of current. Yeah, it's a flow of current which is due to the minority carriers. Yeah, without any incident optical power to this photodiode. Okay, so this is also known as a leakage current. Yeah. Okay, and the third one is known to be a quantum noise. Yeah, quantum noise, and this is basically related to the carrier generation. Yeah, carrier generation. So we're going to see this one by one later on. Yeah. Okay, so thermal noise, the short noise, and also the quantum noise. So basically, I can say that the short noise, yeah, the short noise basically can be is divided into two types. The first one is a dark current noise, and the second one is a quantum noise. Okay, right. Okay, this is to be exact, noise in optical receiver circuit. So we know that for receivers, it consists of photodetectors, photodiode, the amplifier, and also the signal processing circuit. Okay, so in first converting the optical energy, it first converting the optical energy emerging from the end of the fiber into electrical signal, amplify so that it can be processed by signal processing circuit for noise reduction and improving the output file shape. So this is about the optical receiver circuit lah, yeah? So this is the optical receiver circuit. So we are interested on this diagram. Okay, so this is the receiver side, receiver side. So we have the optical signal coming from the fiber, coming from the fiber. So this will generate the electrical current because once we have the optical signal to these photodetectors, the current will be produced. Yeah. So at these photodetectors, the noise that can be generated includes the quantum noise, the dark current noise, and also the background noise and the bit noise. So our interest is only on these first two, the quantum and the dark current noise. And then if we use the APD, yeah, you're going to have the avalanche gain. So this is the base for the APD. If you use the PIN or PN photodiode, there is no avalanche gain. Yeah. So that's why we have a dotted box here, which means that this is only applicable for the APD type of photodetector. Okay. So for this particular case of APD, the noise again will be generated, which is known to be the excess noise due to the gain mechanism, the M, if you can remember, yeah, from chapter 5, the multiplication factor. So this will also create the noise. We're going to learn this later on in this lecture 10. Okay, and then we have this detector load bias. Detector load bias, basically this is related to the R, yeah, detector load. And the noise that will produce is the thermal noise. Okay, and also then the amplifier, in which here we're going to have all of it is the current, yeah. So for this amplifier, we're going to have the thermal noise because we have the resistors, yeah. And we also have the device noise and also the surface leakage current noise, yeah. So our interest will be on this thermal noise, yeah, on the thermal noise and also the device related noise, yeah, for this amplifier circuit, amplifier components. So basically these are the noise sources that can be obtained or that can be characterized for each component of your optical receiver circuits, yeah. Right. So let's have a look at the first type of noise, which is the thermal noise or Johnson noise. So this noise is related to the electron motions, yeah, electron motions due to temperature, external thermal energy, and vibrating ions in the conducting medium. Okay, so this is the source of noise in thermal noise or Johnson noise, yeah. So basically, it is related to the electron motions, okay, electron motions and the vibrating ions in the conducting medium due to this temperature or external thermal energy. That's why we call this as a thermal. Yeah. So because we know that resistors, yeah, resistors, when we have current flows through the resistors, you're going to generate heat. Yeah, we generate heat, and this heat basically will create noise to your circuit. Yeah. Okay, we're going to have this effect. Most of it is in resistors or at room temperature. Okay, so this is the definition of the thermal noise current. Yeah, thermal noise current, the mean square value of thermal noise current, which is given by the 4 kTb divided by R. R is the resistors value. Okay, K stands for the Boltzmann constant, 1.38 times 10 to the 23 joule Kelvin. T is the temperature, the absolute value in Kelvin also. B is the bandwidth of the systems in hertz, yeah. And the R is the resistance that give rise to noise or produce noise. So that's why if we can recall back, based on the previous equation for the bandwidth, B equals to 1 over 2 pi RL times the capacitance total. So we have agreed that if we reduce the resistance load, B will be increased, the bandwidth will be increased. That should be very good. But if we reduce the RL, based on this equation, reduction of RL will increase the thermal noise current, and as such, the noise will be increased. So that is a trade-off between R reduction or load resistance reduction and the bandwidth, and also with the noise current or noise value. Yeah. Okay. And second type of noise is a short noise, in which this is due to the current fluctuation. Yeah, current fluctuation related to the charge carriers. Yeah, the electron and holes. Yeah. It can be divided into two types, which are within the photocurrent. Yeah, photocurrent, right? The first one is what we call as a dark current noise. Yeah, the first type of short noise is dark current noise. So we know that dark current is a small leakage current that continues to flow in photodiode, even when there is no incident light. We have agreed on this. So this dark current will then contribute to the random fluctuations of the particle flow of the photocurrent, and this will be known as a short noise. Yeah, so basically this current will create or will contribute to the random fluctuations of the photocurrent. Yeah, so it's more towards the particle flow or the particle fluctuations. Yeah, or the carrier fluctuations. Yeah, that will be identified as a noise. Yeah. So the equation for this dark current noise, yeah, the mean square of it is given by this. Yeah, where we have the ID is a dark current noise, the mean square of it, equals to 2E. E is the charge amount, B is the bandwidth, and ID is a dark current in ampere. Yeah, so E in coulomb, B in hertz, and ID is the in ampere. So that will determine the dark current value of dark current noise. Yeah. Okay. The second type of short noise is a quantum noise. Okay. So quantum noise is resulted from random generation of electron hole and pairs. Okay. So this is related to generation of electron and hole pairs. So basically it's carrier generation, which is due to the incident light photon. So when we have the incident light photons to the photodiode, the carriers will be generated, or the electron and hole pairs will be generated. Yeah. So the actual number of the carrier pairs generated will fluctuate from the average. Yeah. So basically, the generation of these carrier pairs, yeah, the electron holes, are not uniform. So it will fluctuate. Yeah, it will fluctuate. Yeah, it will randomly fluctuate, and these randomly fluctuations are from the average. Yeah, of this particular carrier pairs generation will then create what we call as a short noise. Okay, so I repeat again. When we have the incident light photons on your photodiode, we know that this will then create the electron and hole pairs, or the carrier generation, yeah, of your photodiodes. Okay, but the thing is that these carrier path generation is not uniform. Yeah, this generation of carrier pairs is said to be fluctuated. Yeah, fluctuated from the average value, and these fluctuations can be determined using the statistical distribution, or to be exact, using the Poisson distribution. I'm going to cover that in detail for this topic. Yeah, it's understood to be based on the Poisson distribution. Yeah. So the deviation or the fluctuation of these number of carrier pairs from the average is known to be the short noise. So the fluctuation itself, the deviation value of these carrier pairs generated from the average value is known to be the short noise. Okay, yeah, so hopefully by now you understand what is meant by the quantum noise source, yeah, which is the deviation, the fluctuations of the numbers of carrier pairs generated from the average. And this is to be based on the statistical method or statistical distribution. Yeah. Okay. So knowing that this is basically related to the carrier pairs generation, so it must be then related strongly to the amount of light incident on the optical detector. So that will be based on the IP, because when we have the incident power, the P naught will create the carrier generation, the electrode and holes, and this will then further create this current, a photocurrent in your photodiode. Okay. So based on that, we can say that the quantum noise current yeah, quantum noise current, the mean square value of the quantum noise current is written to be like this. Yeah, the IQ squared is the mean square. Yeah, mean square of the quantum noise current equals to 2 IP. E is the charge amount, B is the bandwidth, and IP is the photocurrent produced by the average incident optical power, the P naught. Yeah. Okay, same like what I mentioned just now. IP is the output photocurrent of the diode generated by the P naught. Okay, so up to now we have learned about these two types of noise. The first one is thermal noise due to these resistors. The second type is a short noise. Short noise can be divided into two types. The first one is a dark current noise given by this equation, depending on the dark current amount. Yeah, and the second one is the quantum noise, which is related to the electron and hole pairs generated by the incident optical power, and is given by the equations of 2 EB of IP. Okay. Okay, yeah. So hopefully by now you understand the source of noise in your optical receivers. So this will be the equivalent circuit of your optical receivers. Okay. So this is your circuits of the receivers. We have the photodiode, we have the amplifier, we have the load resistors here, and there should be the voltage bias, the reverse bias voltage on your circuits. So this will be the equivalent circuit for this particular component. We have the photodiode, we have the capacitance D, which is the detector capacitance, we have the RL, which is the load resistors, RA, which is the amplifier resistors, and the CA, which is the capacitance of the amplifier. Okay, RS is series resistors, yeah, of the systems. Okay, so if you base on this, we have learned before that the CD, this capacitance CD and CA will then contribute to the bandwidth calculation. The RL will lead to this thermal noise or Johnson noise, yeah, thermal or Johnson noise. RA will also contribute to the thermal noise, yeah. Okay, and then we have the short noise, which is produced in the photodiode itself. The short noise is a quantum noise and also the dark current noise, all produced in the photodiode. So one more thing to be understood here is that this amplifier will create its own noise sources, in which we can state here that the noise sources within the amplifier can be represented by this notation, which is IM, or the mean square value of the amplifier current noise. Yeah, so that should be the IM squared. Yeah, so basically the IM squared, this noise current, yeah, amplifier noise current can be reduced by using a low detector and amplifier capacitance. Yeah, so we can reduce it by using a low detector and amplifier capacitance, which is the C, D, and CA. So if we reduce the C, D, and CA, we can reduce this amplifier noise current. Yeah, so apart from the noise that we have learned before, yeah, the thermal noise, the short noise, we also have this amplifier related noise, which is defined to be the IM squared mean, or mean square value of amplifier noise current. Yeah, right. So we have understand previously about the noise type, yeah, that exists in our optical receiver circuits. So now we are going to learn about the noise calculation and also the signal to noise ratio calculation in your PN and PRN photodiode. Okay, so why we combine this together? Because we have learned in chapter 5 that PN and PRN are almost similar. Between the two, the difference is only PIN is the improved version of the PN. Yeah, so that's why we can join them together. We can classify them together in terms of noise calculation and signal to noise ratio calculation. Okay, so for the PN and PIN photodiode, the main sources of noise are two, which are basically from its own noise in the photodetector, which are the dark current noise and also the quantum noise. Yeah, quantum noise. So both are short noise and the photocurrent. So that will be the main sources of a noise in your PN and PIN photodiode. So the total short noise for this PN and PIN photodiode is given by this. Yeah, because we have learned before that for the quantum noise, or sorry, the I dark current noise is given by 2 EB, yeah, 2 EB of ID. Okay, whereas for the quantum noise, okay, it's quite area squared. So for the quantum noise, is given by 2 EB of IP. So this is the dark current noise, and that should be the quantum noise. So when we have these two noise exist together in your photodetector, so we can combine them together by simply summing up the values. Yeah. So the total short noise current, the mean square of total short noise current, will be simply addition of these two. So we have 2 EB IP plus ID, which is summation of the photocurrent and also the dark current value. Yeah. Okay. So from what we have learned previously from the equivalent circuit, we also have the detector load resistors RL, and also the active element, the amplifier. Okay. That can dominate the noise if dark current value is reduced by proper design of PD. Okay, so in such a way that if we can reduce the dark current amount, we can reduce the short noise value. So as such, when we have a reduction of short noise value, we can have then the effect of noise from the detector load resistors, the RL, and the amplifier will dominate the noise value. And for that particular case, when the thermal noise due to RL and the active element noise dominate the case, we're going to have that the noise generated by these thermal noise and amplifier related noise can be combined by using this amplifier noise figure of Fn. So we have learned previously that for the thermal noise, yeah, thermal noise is given by this equation here, yeah, which is IT, okay, IT squared, yeah, this is the mean square, is 4 KTB over RL. Okay, that should be the equation for the mean square value of your thermal noise. Okay, and in such a way that the thermal noise and the amplifier related noise can be combined together, and this combination will result on just a multiplication of the 4 KTB over RL terms just now with the Fn. So Fn stands for the amplifier noise figure. So that will determine the total noise due to this thermal noise from the load resistors and the amplifier related noise. Yeah, so that will determine the total noise other than the short noise that we have seen in the previous equations here. Yeah, the top equations here. This is the equations for the short noise, and this is the equation for the thermal noise and also the amplifier related noise. Yeah. Okay, so for this, we can calculate the signal to noise ratio for the PN and PRN photodiode, which is simply based on this equation. Okay, so we have learned before that the S over N is given by IP squared, which is the photocurrent squared, divided by the I noise squared, the mean square of the I noise squared. So the IP squared is there. So the noise current in total is a summation of the short noise current and also the thermal noise current and plus the amplifier noise current. So the total noise simply summation of the first current and the second current, which will lead to these equations down here. Okay, so basically the denominator here is a summation of the noise current from the short noise and also the thermal noise. Okay, so that's how we determine the signal to noise ratio for the PN and the PIN photodiode. Yeah. Okay, so this is a comparison of a PIN photodiode, which is depending on the silicon, germanium, and indium gallium arsenide material of the PIN photodiodes. Yeah, so we have the wavelength range for these three types of material. Okay, wavelength range is 400 to 1100 for the silicon. For the germanium is between 800 to 1650, and for the indium gallium arsenide is from 1100 to 1700. That should be the range of wavelength for these PIN photodiodes material. Yeah, responsibility we have higher for the indium gallium arsenide as compared to silicon and germanium. For dark current, the value for germanium is very high. Yeah, 50 to 500, which is not very good actually. For the indium gallium arsenide is very good, about 0.5 to 2 only, and silicon is from 1 to 10. So for germanium it's very high, yeah, dark current value. Okay, rise time, yeah, for the silicon is 0.5 to 1, germanium 0.1 to 0.5, indium gallium arsenide from 0.05 to 0.5. Okay, for the bandwidth, we have a higher bandwidth for the germanium up to 3, for the indium gallium arsenide is up to 2, and silicon is quite small, which is up to 0.7 only. For the bias voltage, almost the same. We have 5 for the silicon, 5 to 10 for the germanium, and 5 for the indium gallium arsenide. So basically, this is a comparison of the pin photodiode for different materials, yeah, depending on these parameters that we have on the left-hand side here. Okay. Okay, so let's have a look at these examples here to test our understanding on the pin photodiode. Yeah. So we are given the silicon type of pin photodiode incorporated into the optical receivers, and this optical receivers has a quantum efficiency of 60%. Okay, so we have the eta is equal to 60% or simply equal to 0.6. Operating at the wavelength of lambda 0.9, so lambda is 0.9 micrometer for the given photodiode. So we are given further that the dark current in the device at this operating point is 3 nanoampere. So ID, the dark current is 3 nanoampere. Okay. And the load resistance is 4 kilo ohm. Yeah. So RL is 4 kilo ohm. That should be your information given. And further on, the incident optical power at this wavelength is 200 nanowatt. Okay. So P naught, the incident optical power is 200 nanowatt. And the post-detection bandwidth of the receiver is 5 megahertz. So it means that the output bandwidth is 5 megahertz. So these are informations given. Determine the short noise generated in the photodiode and the thermal noise in the load resistors at a temperature of 20 degrees Celsius. So it means that the temperature, the T, absolute temperature will be 273 plus 20 degrees Celsius, which will give us 293 Kelvin. That should be your absolute temperature for this particular optical receiver's working operation. Yeah. Okay. So let's find out what should be the determine the short noise generated in the photodiode. Okay. So before we can find the short noise generated, we have to be very clear on this equation for short noise. Yeah. So short noise current is given by the equations of short noise given by ITS squared will be a summation, summation of two effect of current, which is the dark current noise and the quantum noise current, which is given by the equation of 2E B of IP plus IP plus ID. Okay, so this will determine our total short noise generated, short noise generated or short noise current. Okay, in which IP is the photocurrent, ID is the dark current. So in these questions, we are given only the ID, which is 3 nanoampere, but the IP is unknown. IP is unknown. So we cannot calculate the total short noise current because we don't have the IP value. So we need to calculate what should be the value of photocurrent. So for this, we need to use the equation that we have seen before, in which from the chapter 5, chapter 5, we have learned that the responsivity is given by the IP, the output photocurrent divided by the incident optical power. Okay, IP divided by the P naught. All right, that will determine the responsivity. Chapter 5, R is responsivity equals to output photocurrent divided by the incident optical power. Okay, so based on this information, we are given the P naught, which is 200 watt, and part of the component that should be used in calculation of responsivity, in which responsivity is equals to eta, quantum efficiency, multiply with the charge amount, multiply with the wavelength operation lambda, divided by the h, which is the Planck constant, and multiply with the speed of light c. So this will be your responsivity. and this equals to IP divided by P naught. So from here, we can see that the IP can be calculated by simply multiply the P naught and those components that determine the responsivity and E lambda over HC. Okay, yeah. So from here, we can write that the P naught is equals to 200 nanowatt. I think I need to use it here, yeah? Sorry, I need to decide for that. Yeah, it is this side. Okay, so based on this, IP shall be equals to P naught multiplied with eta E lambda over HC. So we have P naught is 200 nanowatt times 10 of negative 9 multiply with the eta, which is 0.6, multiply with E, which is 1.6 times 10 of negative 19, yeah? And lambda is 900 nanowatt, sorry, 0.9 microwatt, sorry, 0.9 times 10 times 10 negative 6. Sorry, I need to repeat it again. Sorry for that, yeah. Okay, 0.6 times the charge amount, 1.6 times 10 power of negative 19, and lambda is 0.9 times 10 of negative 6 divided by Planck constant H, which is 6.62 times 10 of negative 34 joule second. Okay, 34, yeah. And C is 3 times 10 power of 8 meter per second. Okay, so from here, you can calculate the IP, the current, the photocurrent value shall be then equals to 87, yeah, 87.1 nanoampere. So that should be the amount of photocurrent that we have that can be generated by this photodiode of silicon type, yeah. Okay, so from what we obtain here, if we obtain the IP, yeah, we can use it to calculate the total short noise current now. Okay, I'm going to use it now. Okay, in which from the equations here, okay, we can then calculate that the total short noise current, the mean square of it, shall be equals to 2 EB. So E is 1.6, sorry, 1.6. Yeah, 1.6 times 10 of negative 19. IP is 87.1 nano, and your ID is 3 nano. ID is your dark current, yeah. And if we calculate this, your answer for the mean square value of short noise is 1.44 times 10 of negative 19. So this is in units of ampere squared, yeah, because what we have here is mean square value. So that's why the current is ampere squared. So to find the short noise current, simply we square. I mean we find the square root of these total short noise. So we're going to have ITS value, yeah, in which we have determined the root mean square of it. So that should be equals to square root of 1.44 times 10 of negative 19 ampere. So the answer for that will be equals to 3.8 times 10 power of negative 10 ampere. So that should be your total short noise current for this particular case, yeah. Okay, then hopefully it's clear, yeah. And then to find the thermal noise current is straightforward only because we just based on the equation, I believe. Okay. Okay, so let's find the thermal noise current, right? So thermal noise current. Okay, so thermal noise current is given by this equation. So I thermal squared, this is the mean square value of thermal current, equals to 4 KTB over RL. So Boltzmann constant is 1.38. Yeah, 1.38 times 10 of negative 23. Your T is 293 Kelvin. Yeah, and your B is given the bandwidth is 5 megahertz. So 5 times 10 power of 6 megahertz. Okay, divided by the RL, the load resistance of 4 kilo ohm. So 4 times 10 power of 3. So by calculating this value, you're going to get that the thermal noise, the mean square of it is equals to 2.02 times 10 power of negative 17 ampere. Okay, and to find the thermal noise current itself, we need to square root. Yeah, we need to find the root square of this value. So basically, the IT root mean square of the IT of the current will be equal to square root of 2.02 times 10 power of negative 17. Okay, 2.02 root, find the root mean square of it. Yeah. So we're going to have the value equals to 4.49 times 10 power of negative 9 ampere. That should be the value of thermal noise current for this particular case. So if we compare between the short noise current and the thermal noise current, if we compare the value. So for short noise, the current is 3.8 times 10 negative 10 ampere. For thermal noise, the current value is 4.49 times 10 of negative 9 ampere, which shows that for this particular pin photodiode, the thermal noise is higher. Yeah, thermal noise is higher as compared to the short noise. Evidently, it shows by this calculation, yeah, of thermal noise and the short noise current. Okay, then. Okay, so let's have a look at this example again. Receiver in previous example. So we are using the same example as previous. The receiver in previous example has an amplifier with a noise figure of 3 dB. Determine the SNR at the output of the receiver under the same condition. Okay, so we need to find the SNR now. Yeah, we need to find the SNR now. Just now we just calculate the current and the noise current. So now we need to calculate the SNR for the given, for the previous given photodiode. Okay, so for the previous photodiode, we know that the IP. So yeah, okay. So the IP calculated before, the IP is the photo current is 87.1 nanoampere. We have agreed that the total short noise, the mean square of it is equals to 1.44 times 10 negative 19 ampere. Okay, and then we have this the mean square value of the thermal current is equals to 2.02 times 10 of negative 17 ampere. So these are the things that we have obtained from the previous example. And given that the noise figure of 3 dB, so if you can recall back, this noise figure is given by the symbol of Fn. Yeah? Fn, the noise figure is equals to 3 dB. So in terms of linear scale, we can say that the Fn is equals to 10 log of 2. So the linear value of Fn basically is 2. Yeah, that should be the linear value of your Fn. So we're going to use this linear value, Fn equals to 2 in the subsequent calculation. Yeah. Okay, so from the SNR equation that we have seen, SNR equals to the photocurrent squared divided by this, I can say the current due to your short noise, yeah, which is 2EB IP plus ID plus the current, the noise current due to your thermal, and also the effect of amplifier related components. Yeah, so that's why we have the Fn there, yeah, which is the inclusion of the amplifier related noise. Yeah, so that is the combination of thermal noise and amplifier related noise. So we have the 4 kTB Fn over RL. Okay, so further on, we can use this information of the noise current, the total short noise current, and also the thermal current in your calculation, in which you're going to have the IP squared will be then 87.1 times 10 of negative 9 square. That should be the IP squared divided by, this has been calculated before, which is equals to the ITS squared. Yeah, so we're going to have 1.44 times 10 of negative 19. Whereas this 4 kTb, yeah, if we can, okay, this 4 kTb is over L equals to this value. Okay, so it should be plus the IT squared, which is 2.02 times 10 of negative 17, and that should be multiplied by the Fn, which is equals to 2. Yeah, so the Fn here is represented by 2 here. Yeah, as what we have obtained just now, right? Fn in linear scale is 2, so we just multiply this IT square, which is the thermal mean square value of thermal current, 2.02 times 10 negative 17. We multiply it with 2, simply like that. Yeah. Okay, so when we have a ratio of these calculation, the value for it will be equals to 1.87 times 10 power of 2. Okay, that should be the linear scale for the SNR. So in terms of a dB, we're going to have 10 log of 1.87 times 10 power of 2. So the answer for that will be equals to 22.72 dB. So that should be the SNR for the given optical receivers. Yeah. Okay then. Hopefully it's clear, yeah, on the calculation of noise for both short noise and thermal noise, and also on the calculation of signal to noise ratio for the same problems, in which we just need to understand what should be the amount of current the photo current produced, what should be the amount of the total short noise current produced, and what should be the amount of thermal current produced in your problems. Yeah, so that is how you determine the signal to noise ratio for your receivers. Okay. Okay, I think I'm going to stop here. Yeah, and for next lecture, part 2 of lecture 10, we're going to proceed, or we're going to continue with the noise calculation and signal to noise ratio calculation in the avalanche photodiode, which is second types of photodiode to be covered. Yeah. Okay then, so thank you very much. I'm going to meet you again next week. Yeah, for this part 2 of lecture 10. Yeah. So with that, thank you very much. Take care. Going to meet you again very soon. Yeah. Thank you.